I'm happy to say a few words about energy economics today. So we will not speak about climate science or climate emergencies today, not much at least. I think it's a very important topic, and I started this journey actually 20 years ago when I joined our family business, which is in the raw materials, a lot of coal, but not only coal that we handle worldwide. And I started to realize, what energy is and what commodities are, and started to look at the subject of energy economics. I like to start with the importance of environmental protection, and I think, of course, with today's ESG discussions worldwide and our kids, constantly bombarding us with, are we doing the right thing for the future? It is an important subject, and it should not be dismissed in any way. The environmental impact that our lives and that our energy systems have is significant, and we need to do everything in our power to reduce that, right? It shouldn't be political, right? This discussion should not be political. It doesn't matter where you come from, what your beliefs are. We should do everything in our power to preserve our environment as much as possible, right? We should be able to discuss these issues independently of our views. Now, the problem, of course, is that it's become, even in energy economics, has become about respect and ethics, similar as it has become in climate science. Even energy economics, some of the things you're not supposed to say. Yeah? And that's a bit sad. So let's hope, at least in this curve, we can say a few things. Some of you know there are a couple of papers out there, and Bill Smith is on the call as well. He's a co-author and a friend him and I will work together on a few things. The left one will talk today about the full cost of electricity and the energy returns. The one in the middle talks about climate impacts of fossil fuels, specifically coal and gas. And when it comes to the climate science, I recommend two books, and I saw Andy May on the call as well. And I think those two books, many of you know. If you haven't read them yet, please do, and always recommend them. And especially Kunin's book, I appreciate it very much, the independent view. And Andy May's book, also a very interesting view, trying to put both sides of the discussion together and giving a lot of impact and food for thought. Now, back to energy. Where we are today started very much in the past 150, 200 years, because the energy revolution, the industrial revolution that we had 200 years ago, has made a huge difference to our lives. And we all know this. It's interesting, there's this metric to say, would be saying that collective scientific knowledge is expected to double every 10 to 20 years. I don't know if that's true, but what's certainly true is that when you look at World War II, just less than 80 years ago, the scientific knowledge versus what we have today, I mean, we are at a multiple. We know so much more, right? And the argument is that, it took tens of thousand years, to create civilization in Europe, right? It took just a couple of years to modernize North America. And, the first energy revolution at the end of the 19th century came upon us, and really suddenly we could light up our cities, right? And the discovery of the nuclear force gave us even more energy available to us, and we could do so much more. And these are amazing things that happen in a very short period of time. And the argument is that we will reach what I refer to as the next energy revolution. We will, at some point, in my view, have something completely new and different, which we don't know yet, don't yet have. And that may come together with what we call a type 0 civilization versus a type 1 civilization. This is the Kardashev scale, quite interesting one, that basically says the type 0 civilization, where we are today, we're not yet able to harness all the energy available to us in our planet, right? Therefore, we are a sub-global civilization, right? That still uses raw materials. And the type 1 civilization, the next step, some argue may only be away a couple of 100 years, is something where we are actually still limited to our planet, but we are able to harness all energy available to us from the sun and from within our planet. Yeah? And that's just something to consider, that whatever where we are today and whatever crisis we may or we may not see, we will see serious shifts coming in the next 100 years in terms of energy. Okay. So, but let's first talk about today. Global energy crisis. I mean, you all know this. Germany declared early warning signs. This was in March. Of course, now we're 3 months later. We know what happened. Coal shortage in India. I mean, amazing. Last year in September, India was short of coal. Vietnam in March facing summer power crunch as tight coal supply, right? French grid managers asking, oh my God, we're running short of nuclear, there's not enough power. We're having serious problems. This is in April this year. California last year, blackout risks, electricity prices spiking last year, all pre-Putin, right? The UK, of course, big problems. I mean, everywhere in the world, it doesn't matter. This one I love the most. There was not enough coal to produce Teslas in China last year, right? So it's just incredible how this energy situation that started to appear last year, energy crisis, has really spread around the world. And like to understand what's happening, why is that happening? And it's a bit heavy on the text, but I just want you to be aware that 2 years ago, the one of the German universities, Cologne University, put out this interesting paper saying, by the way, in case of a cold winter in 2030, there will be 35 to 70 gigawatt of shortage, a gap leading to 4 to 10 days of power outages. Warning already 2 years ago that the European energy system is running into a serious shortage situation. This is official. You can download this from the university. And then last year, you started to see news releases. Bloomberg, global energy crisis is the first of many in the clean power era. And it's the first time I actually saw this in Bloomberg, especially, right? And making people realize, oh my God, whatever we're doing is seriously affecting our energy supply, right? The world energy system has become strikingly more fragile and easier to shock. Yeah. And we kind of understand why that is, but let's talk a little bit more about it. But basically, the key argument is that the new economy is overinvested, the new economy being green, and the old economy is starved, being conventional, fossil fuel and nuclear, right? So Agora, the German energy institution, government funded, says last year still says, oh, the electricity system works wonderfully on the basis of solar and wind. We don't have to worry about security of supply. New wind and solar plants must be built far more quickly in the coming months. So these are, people that know what they're talking about, kind of know what they're talking about, and they're seriously putting out these information because they believe it's correct. And maybe it's correct, maybe not. I mean, obviously, I think it's not. But let me explain why. So the head of the IEA, Fatih Birol, says solar is becoming the new king of the world's electricity market. So that's the future, right? And then, of course, just last week, The Guardian, Africa must forgo gas exploration to avert climate disasters, warn experts. Right now, Antonio Guterres, UN Secretary General, warned that exploring for gas and oil anywhere in the world would be delusional. So you have this energy war almost going on. You have one side explaining we have to completely eradicate fossil fuels, and the other side saying, you know what, maybe watch out a little bit. Yeah, and of course I belong to that second part. Now, obviously, higher electricity prices cause energy poverty, and energy poverty hurts whom? It hurts the poor, obviously, right? So what's interesting that even during the pandemic, you can see that actually the past 20 years, the global population without access to electricity has reduced from 1.5, 1.6 billion to less than whatever, 800 million. But during the pandemic, because of people being poor, don't have money, energy poverty increased again, right? This is from the IEA. And due to the pandemic, 15 million people, sub-Saharan peoples back then lost the ability to pay for electricity. So definitely, electricity and wealth poverty go together. I mean, it's kind of obvious, but let's just say it anyways. Now, going back to where energy comes from, this is global primary energy. You can see that, until last century, we were all green, right? It was all biomass. We were all burning the European woods and the US woods, American woods. And then the oil age came upon us. Lucky enough, we had a lot of energy. The coal age came upon us. Then oil came, then gas came, nuclear came, a bit of hydro, and now, of course, some of those renewables. So we have multiplied our global energy supply. This is primary energy. And today, fossil fuels still make up 80% of that energy supply, right? Oil, coal, and gas, in order of importance, it's 80% of global energy. Wind and solar is about 3%. However, the primary energy metric is a very difficult one to really put wind and solar in there. So that's a separate discussion. You can read in the paper why that is. But the fact is that wind and solar is minuscule in a global sense. Okay. The question is what happens in the next 30 years. So my argument is we're going to grow 50%. Very simple, driven by energy per capita increase and population increase. But there's a 20% per capita energy per capita increase we project as people become richer, as poorer nations become richer, and population continues growing, and that's 50%, period. Yeah? There is what's called a Gerunds Paradox that says that any energy saving will always be offset by increased energy demand for other things. Computers, like flying to the moon, whatever. So as we become more efficient in lighting ourselves, there'll be new things. We just have 3 phones instead of 1 phone, consuming the electricity we just saved somewhere else, consuming that now. Now, looking at these 170,000 terawatt hours of primary energy, you can see that that's roughly 40% used for electricity and 60% used for heating, transportation, and industry. All right. And electricity is actually 60% coal and gas. Okay, so while coal and gas make 50% of primary energy, they actually make 60% of electricity. So when our bank asks us, okay, what's your fossil fuel exit strategy? I'm like, okay, what's your lighting exit strategy, right? Because 60% of electricity comes from coal and gas, and exiting them would be a very bad idea, obviously. Now, when you then look at the net zero pathway, this is the one from the IEA, and they're all similar in a way, put out last year. You can see that the primary energy projections that they have shows, oh, actually, you know what, we're going to reduce primary energy 10% in the next 8 years. That's the net zero pathway of the IEA. And whatever pathway you read, they're all similar to that. The argument is always that we will reduce less energy in total, despite population increase, despite people becoming richer and needing more energy. Of course, completely unrealistic. Secondly, they always have an assumption that there's a huge amount of wind and solar, part of primary energy. Germany today has 5% of wind and solar after 20 years and billions of investments, and the whole world on average in 28 years will have 40% wind and solar. It doesn't matter what you believe in global warming is, but this is obviously unrealistic, to be kind. Yeah. Now, looking at electricity now alone, you can see this is the electricity growth over the past 6 years from the IEA, 7 years from the IEA, and you can see that electricity grew every year. This is here the red dots in terawatt hours. We're starting at whatever, 25,000 terawatt hours. You can see growth, except for COVID, small decline. And then, of course, post-COVID, huge increase in electricity. Okay. Interesting also is that the increase in 21 came to 60% from coal and gas, 50% from coal. So coal share in electricity is actually 36% globally. But last year, 50% of the increase came from coal. So coal's share increased, not only in absolute terms, but also in relative terms last year. And of course, going forward, everything is going to be green, right? Obviously. Interesting is also that you see when a lot of growth is happening, you need fossil fuels. When little growth is happening, you can manage with the growth with green energy. Because when there's little growth, you can kind of replace a little bit here and there, put some extra solar panels up. We're going to burn a little bit less coal. It's going to be fine. But as soon as you need growth, you're going to need something reliable. And that reliable can only be, dispatchable power, right? Nuclear, coal and gas, basically. So this is just to put into perspective those numbers you see and that fuel the press reports we read, right? Because these are serious reports from the IEA, and that's where the press takes the information from. Yeah. Now, I want to introduce the concept of energy return of investment, and many of you already know it, as Jim mentioned. Obviously, we're familiar with the money return of investment, right? $1 in, $2 out. Hopefully in 2 years, we're happy, right? Now, the same concept exists in energy. You have to understand that producing energy takes energy, right? We need first to deploy energy to somehow get energy later, yeah? And whatever you deploy versus what you get out, that's called energy return of investment, right? It's an eROI, just a multiple. Now, basically, energy returns actually measures the net energy efficiency, right? The eROI actually measures the global net energy efficiency, because it puts everything together, just measuring only energy, not dollars, right? Not materials, not tons, just energy, okay? And of course, as we become more advanced in society, we require higher energy efficiencies. Right? This is from Prieto, is a book from 2013, a very one I recommend, focusing on Spain, but just explaining that as we become more sophisticated, you're going to require higher energy returns, right? The same logic goes here, right? The approximate eROI required, right? I mean, we didn't need much back then, but if you want to fly to the moon, we need a lot of energy efficiency. That's why, gasoline and fuels, I mean, oil fuels are just very energy efficient and dense as well. Yeah. So solar modules, by the way, are somewhere here, right? And modern society actually requires this. Just gives you a sense how important the eROI factor is. And now looking at numbers, not really, but the most energy efficient, highest eROI is probably nuclear. They have the least input for the biggest output. There's some papers out there that talk about the 70 or 80 eROI. I think that's a bit much, but it's a very high number. The second most efficient appears to be hydro. Hydro appears to be very energy efficient in terms of just putting up energy, putting up the dam, but once it's there, then it runs quite well. The third is probably thermal, right? Coal and gas. Some people talk about 20, 30 times energy return on investment. Also seems a bit high, but anyways, it's relatively high. Now, you may argue, why are we doing coal and gas and not the more efficient one? Well, it has to do with the cost, right? Nuclear actually tends to be very expensive. And coal and gas actually is the cheapest in full cost of electricity basis. Now, what's interesting is when you go green, you will find a very low eROI. That means the energy needed, the input terawatt hours or gigawatt hours, whatever, to put in to get out is very, very high. And actually, it turns out to be the most expensive. And it's only the most expensive if you actually look at the full cost of electricity, not at the marginal cost of electricity, which is levelized cost, right? LCOE is mostly used in the press. And levelized cost of electricity, I explain later, is a partial marginal cost measure, while the full cost measure shows you everything, including backup systems and transmission and balancing and all those things. Now, most importantly is that the minimum eROI that we as a society require is probably in around 6 to 10 times, whatever, roughly. Below that, we're going to have a bit of an issue. And most renewables are below that threshold. And that is actually the underlying reason why the world is starved today of energy. Because we have been putting all our money into this low energy efficient way of producing energy and taking it away from the left side. Not all of it, but a lot of money. I mean, I get my point. Now, by the way, the Romans used to have a 2-to-1. The Romans were the most advanced society prior to Industrial Revolution, and they had a 2-to-1 energy return of investment. And that also limited the size of their cities. The Roman cities couldn't grow beyond 1 million because they couldn't energy efficient enough get the food and the product into the cities, right? And only the coal power enabled society to develop beyond that. Yeah? Now, of course, technology will improve all of these. And the second more important point is actually that the material input, right? The material input per output is very efficient for nuclear and coal and gas and very inefficient for wind, solar, biomass, and hydro. So the number of just raw materials, resources required to put all this up is also a second important environmental concern for our energy systems. We want to be efficient, not inefficient, in material use as well. And of course, then there's a space requirement, obviously, right? So the space required for nuclear, coal, and gas, relatively little. For hydro is much more. And for wind, solar, and biomass, we all know it's very, very high. On the material ones, I refer to an old paper from, or information from the Department of Energy in the US, that's just showing the base material input per 1 terawatt generation. And by the way, when they say base material, they put cement, copper, glass, steel, but all of these are actually not the raw materials, right? The raw materials are a multiple of this. The iron ore required, the coal required, right? To even make glass or steel or copper or cement or aluminum. That's not even counted. So there is some information around this. It's not yet, I would say, very well covered in the scientific press, and we're trying to get some more into it. But it's interesting to see just the scale about the material input required, just build the capacity. Of course, a solar panel doesn't consume gas building electricity, while a gas plant then still requires gas. So of course, over the lifetime, there will be a bit of catch up. And of course, in the space requirement, you're all aware that, there's so much more space required for the same, this is to power a flat screen TV by energy source, right? Hydro needs a lot of space, right? Wind needs a lot, solar needs a lot, and coal, nuclear, and natural gas need very little space. I think it's quite obvious. Now, what's interesting is that if we do carbon capture and storage to decarbonize, of course, what do? We need energy to do that. So we reduce our energy efficiency doing that. The same way, if we do hydrogen, we will now take the least efficient way of producing energy to produce hydrogen, which costs at least 60% of energy again, without storage and transportation. Just to produce and use hydrogen, you roughly lose 60% of energy. So suddenly, we're here. So of course, our costs increased, obviously, right? Our material efficiency has reduced, and now we're closer to the Romans. I think that's where we want to be. Great, right? So you get my point that actually we are moving from this to save the climate. But today we don't talk about climate. We just talk about energy efficiency and what it means, and why the world is going into energy starvation if we do not dramatically and quickly increase our investments in the left side. And talking about investments, this is the global electricity generation. Remember, 36% is coal, 20% is gas, so 60% roughly is coal and gas, of what is 28,000 terawatt hours. And this is the investments, right? Coal gets, a fraction of the investment, and wind and solar gets almost half of the entire global investment in energy supply. And that's the problem, right? These numbers are from the IEA. So again, the new economy is overinvested, the old economy is starved. Okay, taking one step further, laws of energy. You remember your physics class, first law of thermodynamics, very easy. Energy is never lost. Okay, easy, right? Before, after, always the same. You just transfer energy from one form to another. We never lose it. The second one is interesting. I always have to keep reading up on it as well. But basically it talks about entropy, whatever that means. Basically, it means that whenever energy has a tendency to lose useful energy, right? So energy dissipates in a way. It doesn't get lost, but it loses value. And that's called what entropy, right? High entropy is low value, low entropy is high value. Yeah. So, and that's the conclusion from that is actually whenever you touch energy, you convert it or you store it, you always lose useful energy, right? Just explained with the hydrogen, right? I mean, you have useful energy, solar, and now you try to make something out of it, you just lose 60%, gone, right? By the way, taking one step back to the hydrogen part, very important one. What would you use to produce hydrogen? You would never use coal power. You would never use gas power. You would never use nuclear. You would never use hydro. Why? Because why would you throw away 6% of energy? You just use the energy when you need it. So you would only use wind and solar. In fact, you would first charge your Tesla with your solar panel before you produce hydrogen. Again, you don't want to lose 6% of energy producing hydrogen. First, you charge the Tesla, and then you use hydrogen. So that means you only use the underutilized excess, too much capacity from wind and solar alone to produce hydrogen. And how much of that do we have? And will we have? And where will we have it? Right? So this whole hydrogen discussion is a very interesting one, but logically it doesn't work. Because logically you would only ever use something that you have in excess of, and you would only use the green stuff. You would never use something else. It would just be a waste. Yeah. And when you think about that, you start to realize, actually, it doesn't make sense. It doesn't. Yeah. So of course, the laws of energy do not follow the laws of computing. I mean, Moore's law, things get better and better. It's not energy, it doesn't work like that. Now it's a bit more complicated. I want to show you something from the IEA again. I love the IEA, reading those reports. So you see that this is China's energy supply, and you can see that blue is thermal. The energy, China gets all its energy from thermal, right? And a bit of hydro, of course, and some bit of wind and solar. Right? And then they have peak and capacity and adequacy. They again get it from thermal and hydro. And then they have the ramping flexibility, right? So it's a medium-term ramping up and down, which comes primarily from hydro. Okay, and of course some storage. And then they have stability, right? To keep the system stable. That comes primarily from thermal. Now, as we shift into the new energy system, the IEA models by 2060, the system will look like this. A lot of colors, a lot of inefficiencies in there. will all come from wind and solar, right? Nuclear will give me stability. Thermal will be completely gone. I mean, just think about the second law of thermodynamics, the first law of thermodynamics. What happens if we go there? How much more energy is required to just get there, right? The IEA says itself, shifting away from a centralized thermal power plant technology makes our power system more complex. They didn't say that results in a huge waste of energy, because more complex system means more dissipation of useful energy, right? Curtailing renewables. Vietnam just put out no more wind and solar power sources to be added this year. Okay. Australia, AEMO suspends new wind and solar projects to deal with market crisis. In the US, the MISO, I met the president myself, reports that, yeah, maybe we can conclude upwards of 50% renewable share in our system might be achievable. When you talk 101, they will never say that. They do say beyond a 30% renewable penetration, oops, where's my mouse? No. Yeah. Beyond the 30% renewable penetration, the system as a whole is facing new and shifting risks rather than simple local issues. In other words, there'll be trouble, right? And here they talk here in the same, the MISO has this report, they talk about renewable integration complexity. As the complexity increases logarithmically, the higher the share of renewables in the system, of intermittent renewables in the system. That is why the cost of electricity increases logarithmically as you increase the share of wind and solar in the system. Now, looking at Germany, my own country, we are all aware it's probably the highest electricity prices of the Western world, 5 times higher than China, 2.5 times higher than the US. Now it's even more because now I think we are here at like 250 euros now a megawatt hour or something. It's crazy. And why is that? Well, this is Germany's installed capacity over the past 20 years. And you can see that Germany used to have 115 gigawatt of installed capacity. Today it has double, 220 gigawatt of installed capacity. And all that was added was all wind and solar. Wind and solar installed capacity is now more than half of the total installed capacity. Of course, the fossil fuel capacity actually stayed the same. Nuclear went down, right? They're supposed to turn off the rest of this year, but I hope they're not going to do that. So you can see what happened, right? You can see that with this doubling in capacity, Germany managed a 30% share of electricity generation. So electricity consumption is stable. And now wind and solar make up about 30% of electricity. So they doubled the capacity. That gave me a third of generation and 5% of primary energy, roughly, right? That's what happened. And that is why Germany is in the trouble they are today. And not only, but also because by doing this, they said, you know what, in the meantime, we can just buy our gas from Russia and the coal as well, right? So we make ourselves completely reliable or dependent from Russia. Russia used to have a 30% gas supply share 20 years ago. Today it's over 50%. And if Nord Stream 2 had come online, it would have been 75% of gas supply from Russia. So the energy economy, the policy completely forgot about the reliable supply, focused only on wind and solar. And like, you know what, everything else is not important. But now it becomes important. Yeah. The world, by the way, has 8,000 gigawatt of installed capacity. Now, what's interesting is that when you look at the world of this 8,000 gigawatt of installed capacity, but that includes coal, gas, nuclear, hydro, everything, right? 2019, about 1.5 terawatt, 1,500 gigawatt was installed capacity on wind and solar. In March this year, we reached 1 terawatt of solar. Now, the BCG has made this study that I'm quoting right here in June last year. It's about mastering scale in renewables. And they're projecting that by 2030, we will need to add 8 gigawatt of wind and solar. We need to double our installed capacity in the world in 8 years. What Germany has done in 20 years, just for Germany, the world needs to do in 8 years. This is to reach the net zero pathway. And then 10 years later, another doubling. And 10 years later, again. So everybody knows that number one, the net zero pathways have nothing to do with reality in terms of energy consumption, energy supply. And this is what, if it was serious, we would have to do this in terms of our supply or actually generation capacity. And of course, I'm saying very clearly, we will not have enough materials. We will not have enough energy. We will not have enough space to build this. Right? There's actually not enough energy to build this. Right? So, but Fatih Birol from the IEA says solar is becoming the new king. Of course, it's getting the biggest money. That's why the new king. So definition of king of electricity is now about who gets the most money. It's not about who gives the most value to our energy system, but who gets the most money. That's the new king. Now, we're all aware of what capacity factors mean. This is the global wind map without the US. Sorry, guys. And you can see that, of course, the north and the south tends to have a lot of wind, the bottom as well. There's a new paper that Bill Smith and I are working on wind specifically, very interesting one. I learned a lot. And you can see that actually the central part of the world, especially Asia, has practically no usable wind. There is no wind. India, China, Indonesia, Africa, there's no wind. So I don't know where they want to build this wind capacity, okay? But they want to build it somewhere. Probably all up here somewhere and all here. And then I don't know how they get electricity where they want to get it to. Now, the global average capacity factor is 21 to 24% for wind. Europe, you reach maybe 35%. 40 if you're very lucky. That's a natural capacity factor. And of course, in Indonesia, you probably have 8%. I don't know, nothing. There's no wind there. Now, this is the global solar map, the solar irradiance map. And you can see, of course, again, without the US, sorry, guys, Australia very strong in sun, right? South Africa very strong, of course, the Saharan desert, and of course, California very strong in sun. But you can see again, Europe very little, China very little, even Indonesia right in the middle very little, and of course even middle of Africa because of the monsoon. People forget that there's a lot of rain, right? So where are you going to put your solar? Australia, okay, great, right? So you just look at the natural conditions, you even have trouble, and the average capacity factor is 11 to 13% of solar PV. In Germany, it's 11%. That's the average capacity factor for Germany. In California, you reach 25%. In Australia, you may get close to 30% if you're lucky. Capacity factor means, obviously how much energy, how many hours of the year do you actually use your solar panel or your wind bill? Because otherwise there's no sun at night or there's no wind, whatever, in the summer. This is Germany's solar and wind generation 1 month, 2 months ago. And you can see that Germany had installed capacity of 65 gigawatt of wind. And for 2 weeks period, there was 3 gigawatt roughly on average. That's a 5% capacity factor. The average capacity factor in Germany is 24%, but during those 2 weeks it was 5%. It was very sunny, as you can see, there's a lot of sun, but at night, even in Germany, still no sun at night. We're still hoping for that to come at some point. So let's say Germany tenfold increases wind capacity. I don't know where, but let's say they do it. Okay, then we have 30 instead of 3, right? Still a bit short. You see the problem. Now, wind and solar, variable renewable energies, have limiting factors which are not in dispute. They have a low capacity factor, natural capacity factor driven by nature, right? They don't have a high energy density, they have very low energy density, right? There's a low availability of wind and solar, and per square meter, there's actually only so much energy that's coming onto our planet in form of wind or in form of solar. It's very little, okay? The energy efficiency is actually very low, right? Conversion, conditioning, transmission, all these things require energy. There's very low energy efficiency in the system. Wind and solar resources are actually correlated, right? So when it's low wind in Europe, it's low wind everywhere. Night, it's night everywhere, right? Except, other side of the globe. So there's a high correlation in the resource, wind and solar, for large regions. They have a very short lifetime, right? I mean, wind farms, obviously, especially in the sea, don't last 15 years, right? Solar panels, maybe 20 years, but then they will probably be changed, refurbished, right? They all require 100% backup and storage, obviously. 100% always needs to be there, backup and storage. They have a large mineral resource requirement to build the capacity, which needs to be rebuilt every 20 years because they have a very short lifetime. big recycling issues because of this large space requirement with large materials. You need to recycle them every so often. There's a big issue with that. And of course, in total, the eROI, the energy return of investment, and the material efficiency is very low. Now, why do I name all this? Because basically, there is a benefit to wind and solar. It reduces the amount of coal and gas we produce and combust. And with it, the CO2 emitted during combustion, assuming no increase in energy demand. That's it. Right? So these things on the left, they're not in dispute. These are all the costs we take upon ourselves to try to reduce the amount of coal and gas combusted, to reduce the CO2, to hopefully reduce future temperature, to hopefully reduce bad weather events and sea level rise. That's the chain, right? But of course, assuming we don't increase energy demand. I mean, it's unbelievable that people don't make that simple logic conclusion. Just look at this left side and then look at what benefit you're getting, right? Now, we talked about cost of electricity. So the cost of electricity generally in the press assumed is what we call levelized cost of electricity, which includes the cost of building, the cost of the fuel, and the cost of operation, right? That's LCOE. What is not included is the cost of transmission, conditioning and balancing, the cost of storage, and the cost of backup is not included in the LCOE measure. What's also not included is the cost to the environment, the cost of recycling, and what I call room cost, actually the cost of the space, because using so much space has climatic effects, has impact on plant life, on animal life, all those things. There's costs to using so much space, right? So obviously LCOE is incomplete, but most of the time what you read in the press is based on LCE. When you see it's cheaper, right? And then there's the other factor. We talked about material input, we talked about the lifetime, and we talked about the resulting low energy return of investment. So when you look at all of these metrics and then you really compare the cost of renewables, variable renewables versus conventional, obviously conventional is much cheaper, always. And in fact, the higher the penetration is of wind and solar in the system, the cost will logarithmically increase, right? So we see these things from Wood Mackenzie here for Vietnam. We see coal is very cheap, gas is also cheap, but now solar will become cheaper and wind will become cheaper. That's what you see. But again, you cannot compare base load with intermittent load. It's misleading. You are missing what we call integration cost of VRE, right? You're missing all the other things back there on the previous slide. And if you include them, then the cost will be skyrocketing high. That is why costs are so high they are today. That's why Germany has these high costs, because people never really calculate the total cost. They always calculate the marginal cost. Yeah. The IEA themselves say the system value of variable renewable energy decreases as their share in the power supply increases. It's a very nice way of saying it's going to be more expensive the more you put up. I mean, they all know it. Doesn't matter which energy economic institution you go to. So let's take a step back. What are humanity's key challenges? I mean, you all have our view. I think food and water is certainly one key challenge we still have, right? And there's a problem with it because the food and water supply pollutes or overuses our resources, our pollution, our soil and our water, right? Then there's a big thing about energy, right? Energy, the main problem is probably pollution of air, right? And also extraction of resources. And then there's, health, bodily, mental, and spirit, right? I mean, what's the main issue is probably inner peace. It's a peace in general. If you're all mentally healthy, we wouldn't have any wars, right? And the fourth one, I argue, is the waste, right? The pollution our life generates, right? These are serious challenges for our world. And obviously, most of these are about energy, if not all of them are about energy, right? Energy is at the core of everything that we do. And if you start to play with our energy systems, we start to play with the basis of humans' existence. Life will continue. The world's not going to go under. It's just going to be more expensive. People are going to die. And that's it. And the poor are going to stay longer poor, right? And energy is at the core of all of this. Yeah. So the environmental impact of energy systems needs to be reduced. We need to look at the production of our raw materials and reduce the environmental impact. We need to look at the processing of the raw materials, right? We look at the transportation. And of course, you look at the operation, the combustion of what we do with the raw materials to produce energy. And then there's the recycling, right, after the useful life. These are the basic value chain of our energy systems we need to look at. And of course, we need to reduce the environmental impact. And the impact includes emissions and includes non-emissions, right? There's emission impact to the environment, and there's non-emission impact to the environment. I mean, greenhouse gas, you can call emissions. Some of them are emissions. I mean, it's fine. Let's not argue about that, right? But there's other things, right? There's SOx, NOx, mercury, chlorine, particulate matter. There's many, many issues that we blow up in the air. Yeah. Then there's non-emissions. There's the energy input. There's the raw material requirement. There's the space requirement, the waste generation, the animal and plant life, the health and safety. All those things are non-emission impacts of our energy systems to the environment. But what do? We focus on operation. Actually, we focus only on combustion. What do we do? Now, let's just focus on CO2 only, right? Let's just pick from all of these issues we have, let's pick CO2. And obviously, by doing so, we will distort and create undesired consequences. Obviously, everybody understands that, right? I mean, if we pick one of these and price one of these, but we don't price the others, we're going to lead to distortions, right? One example, by the way, is the switch from coal to gas for climate reasons, because gas emits half the CO2 that coal does, which is true. But when you include the methane as per IPCC data, suddenly it becomes the same. Because we're not looking at methane, just one little element, suddenly our whole energy policy changes. The whole world switches from coal to gas. My bank asking me, when are you going to get rid of coal? I ask them, when are you getting rid of LNG? Yeah. it's incredible, right? So how can we allow energy policy to look at one little bubble and not look at the whole thing? And everybody you talk to will agree with this, but then they go back and do their own thing again, and they cause environmental and economic distortions, which we're seeing now. Don't have to tell you that, of course, any carbon taxation is wrong. It hurts the poor, right, more than the well-off. This is from Willy Eschenbach, right? And he writes, I mean, you know, he goes a bit further. He says a plot against the poor. I don't know if it's a plot, but the fact is that carbon taxation is wrong. Not only because it distorts and gives wrong focus, but also because it hurts the poor. Right? So, and hurting the poor is not the only disadvantage, right? It also hurts the environment, as mentioned. So look, the positive news is since the Industrial Revolution, we all live much longer, about twice as long as we used to. So we have done an amazing thing, right? I mean, the world has developed in a very, very positive way, and mostly thanks to energy, to available, affordable, reliable energy. And poverty has gone down despite this dramatic increase in population. Poverty is down to levels we've never seen, except for the past couple of years because of COVID increased again. But generally, we're in a very, very strong positive path. Why can we not share these messages? I mean, I know you guys do. Yeah. So the triangular objective of energy policy should be security of supply, affordability of supply, and environmental protection. Right? Environmental protection, you can argue climate is part of that, fine. Pollution, plants, animals, land, space, material input, energy, but it's all environmental concerns. And let's now look at wind and solar, right? It's not secure, it's not affordable. I even question its environmental positivity, right? So how can we allow energy policy to dismiss that? Again, independent of what your view is of climate change. Right? Put any price to climate change, but at least compare the two, right? And then, of course, The Economist just recently said, oh, we just realized the Green Revolution risks running short of minerals, money, and places to build. And energy, I would add, most importantly. There will not be enough energy. We are running into shortage. Beautiful for fossil fuel companies still in business. Beautiful for power plants still in business, if you're allowed to, right? So what is the future of energy now that we've seen all what's going on currently? I don't know, but I would say we have to invest in basic research, right? We have to, at some point, I argue we will wean off fossil fuels. I mean, next 1,000, 2,000 years, I mean, at some point it will run out. Not now, not 100 years, not 200 years, we have enough. But we cannot forever do that. We need to figure something out. I don't know what, right? And we need to invest in generation, material extraction, processing, storage, conductors, recycling, all those things need to be invested in. Right, and the future will be something with the nuclear force, probably. I don't know. Yeah, and probably about the power of the planetary system. I mean, there is a lot of energy out there. Nothing to do with PV will not work, right? Photovoltaic will not work today. But maybe there's something else. I don't know how, right? And of course, there's a lot of energy within our planet. Today, geothermal is not energy efficient either. But maybe at some point we'll find a solution. I don't know, right? I mean, such new energy systems may be completely new, presently unknown energy source, right? We argue in our paper that was recently released. One thing we have to remember that whatever energy system we have, we will always warm our biosphere, right? Because all energy does what? It ends up in high entropy, low value heat, going into our biosphere, warming our cities, right? I mean, it's not much compared to the energy of the sun, but it's still significant. You can read it, you can measure it, right? I mean, part of the measured increase in temperature comes from exactly that, the urban heat island effect, which is nothing but the energy we consume in the city of Milan makes Milan 4 degrees warmer than outside. Of course, it's also about wind and all those things, but there is the energy that comes from, right? And then second, we need to actually invest in our existing energy infrastructure to make it more efficient and to reduce your environmental burden. We have to invest, not divest from what works until we have found a solution. We don't have a solution today. Obviously not. Wind and solar is not the solution. Hydrogen is not the solution. Purely economically and environmentally, very clearly, in my view. Yeah? We need to reduce the waste we generate, right? Waste to power, all these things, reduce the poverty to, I mean, whatever climatic change we have, we weather them with energy, right? So we need more energy. Yeah? Reduce poverty. The poor are going to hurt more from a hurricane than the rich. Yeah? So if investments in fossil fuels will not increase substantially, we argue, a prolonged global energy crisis is difficult to avoid this decade. We are running into energy starvation in a very, very serious way. And of course, Putin has made it worse, right? But that gives also the reason now for politicians to do what they do. In Germany, we go back to coal now. Yeah. So I think it gives you a sense. It's very simple. 2 things: invest in research to find a solution, and 2, until then, invest in what you have to make it better, cleaner, and faster, and whatever. Very simple, right? So in summary, there's a fundamental underinvestment, logical. Where do you put your money in the future? Exactly in here. That's where you're going to make money, right? Today's renewable come with a lot of inefficiencies at grid scale. At grid scale, they lead to energy starvation, right? Talked about intermittency, energy density, material input, all those things. The entire supply chain counts, right? The current sole focus on combustion operations is wrong. It destroys, it's costly, costs the environment and costs money, right? Emissions are only part of the problem. Obviously, there's material input, energy input, space requirement, recycling, all those things. Yeah. By the way, the world extracts 90 billion tons of material every year. Almost 100 billion tons, including 8 billion tons of coal, is being used to sustain our life. It's a lot. Yeah. Coal, gas, oil, and nuclear are urgently needed until what we call the new energy revolution. Right? Environmentally sound is to invest in, not divest from conventional fuels. That's the best you can do for the environment. Right? So the current energy crisis is caused by the underinvestment. That's it. Very simple. So I would love to have a discussion with you now, but basically I'm done. You can ask me any questions, also contact me later. I do from time to time speak about these things at various institutions, and especially at banks, people are very interested to understand, wow, I didn't realize this. But you cannot argue with many of these, maybe some of them, but I'm happy to be challenged, honestly.